So does that also work? Yes. So okay, now after having solved the technical difficulties, hopefully, today I'm going to talk about ref tables. I'll mostly cover what ref tables are, where we're going with ref tables, and also why you should actually care about ref tables in the first place. First, I want to introduce myself. I'm Patrick Steinhardt. I started diving into Linux in 2002 when I was 11 years old. I was back then basically just like fiddling around with compits and also breaking my computer with what my dad said back then must be a virus because it's free. But this eventually kickstarted my interest in open source software overall. And I then made my first open source contribution back in 2011. So when I saw an open position in 2015 that was about contributing to open source projects and version control systems in particular, I immediately jumped on that opportunity, and starting in 2015, I then became a contributor to both Git and also libgit2. In 2020, I eventually switched jobs where I have been working at GitLab as a backend engineer, where I was working on both Git and also Gitly, which is basically the backend for all Git things at GitLab. And nowadays, I'm the engineering manager of the Git team, which is solely focused on Git upstream development. So despite my contributions to Git, I also took part in the Gerrit Hackathon in Berlin in 2016, which was hosted by my then employer, Allego Software Solutions GmbH. So I have a single commit in Gerrit that is only about changing the font size in some kind of UI. So hopefully that actually qualifies me to actually speak at the Gerrit User Summit today. But yeah, that's enough about myself. Let's first a little bit into what ref tables actually are. This might not be anything new for a couple of folks in this room, but it doesn't really make sense to talk about ref tables if you don't understand what they actually are. Before talking about ref tables, though, let's first talk about how references are stored in Git in the past. When creating or updating references, they are by default, microphone is doing weird stuff, they are by default stored in the so-called loose format. So every reference is stored as a separate file. The reference format itself is quite easy to understand and also easy to grasp. So to demonstrate, let's first create a simple repository with a commit and a branch. The first file will examine is head. This reference indicates the currently checked out commit in your repository. As you can see, it has a refs column prefix, which basically indicates that this is a symbolic reference where the target is refs head's main. So we know that we have the main branch checked out in this repository. All the other references are stored in the ref/directory hierarchy. So as we can see, we got two files in here, in refs heads, which is named in feature and main. And these are our main branches in the repository, and both of them have an object ID that they're pointing to as contents. Now, storing every single reference in a separate file doesn't really scale well when your repository has hundreds or even thousands of references. So it becomes really inefficient at that point in time, because every single reference needs a separate inode, and that typically means that you would have to store it in a full disk sector on your file system. And also listing your references becomes increasingly expensive because you have to open like thousands of files. So to counteract this, Git regularly packs your references into the so-called packed refs file. You can manually pack your references by executing git packed refs --all, which you don't typically have to do because Git does that automatically as part of Git maintenance, which it runs after like several other commands. But as you can see, before and after executing this command, both of our loose references have now vanished. And instead we have a packed refs file that is simply a sorted list of all the references that have just been packed. Ref tables are an alternative backend for storing references in your repository. So let's again create a repository, but this time with a ref table backend by saying --ref format equals ref table. First, we'll have a look at head again. As you can see, this file still exists, and it looks like a symbolic reference, but it points to refs heads.invalid. This file really only exists because of compatibility reasons. Git does not consider a repository a Git repository unless it has a head file in there. So we don't use it, but it has to exist. The second step we have in this repository is refs heads. In contrast to a normal repository, this is not a directory, but it's a file that contains just some garbage. So if a Git client tries to read this repository with a files backend, then it would be expected to fail as a safety mechanism. Last but not least, the Git configuration also looks a little bit different in this repository. Most notably, it also got a ref storage extension with the value of ref table, which basically tells us that this repository is using the ref table format. The first data structure that is specific to ref tables is the tables.list file. This file tracks the currently active list of ref tables in that repository. So whenever you update a reference, Git will write a new ref table and append it to this specific list. This mechanism is quite important because it allows for atomic updates in a repository. You can get a consistent snapshot of all the references by reading the tables.list file and then loading all the referenced files. And you can also do an atomic update of multiple references at once by first writing a new table, appending that new table to the new temporary tables.list file, and then atomically renaming that tables.list file into place. The tables themselves are stored in a binary format. While a binary format is more complex than a text-based format, it also allows us to store the data more efficiently in the repository. So we won't really dive into all the intricate details of how exactly this format looks like, as that would lead us a little bit too far down the rabbit hole for today. But if you squint really hard, you'll still be able to see a couple of things in these tables. First, we've got a ref prefix that indicates that this file is a ref table indeed. We also got something that seems to be a footer, which is indicated by a second ref string in that whole table. You can also see our head reference in that table, which seems to be a symbolic reference where the target is ref's head's main. As I've mentioned already, Git will append a new table to your tables.list file whenever you update a reference. So when we create a new commit, you can see that our tables.list file now has two entries, the old table that we already had beforehand and the new one we just wrote. So let's inspect that table with another hex dump, and we can again see some interesting things here. We've again got the ref header and the footer. We've got our ref's head's main reference in there, and that reference is now followed by the object ID of the newly written commit. As you can see, this object ID is not encoded in hex as we have in the files backend, but instead it's directly written in binary, which is more efficient as a storage mechanism. Of course, we cannot just keep on appending new tables to the tables.list file whenever we write a new reference, as that will quickly get out of hand if we had hundreds or even thousands of tables. To prevent the list from growing too long, we basically use autocompaction. Whenever we append a new entry to the tables.list file, we basically figure out whether some tables should be merged together. So let's create another branch here. As you can see, this time around, we didn't append a new table. Instead, we end up with a single merge table that contains all of the references. You may have noticed that each of the tables has two increasing counters. On the left-hand side, we have the minimum and the minimum update index of the records contained in that specific table, and the right-hand side is the maximum update index of the contained records. Before, the first and second update index for each table was always the same number. But now that we have merged multiple tables into one, we can see that the first one contains the minimum update index of the tables we have merged, and the second update index is basically the maximum update index of the merged tables. The RefTable backend uses geometric sequences to decide whether or not tables should be merged together. So each table must be at least twice as large as the next one. If that geometric sequence is violated, then we will merge together as many tables as required to restore that property. You can see this property come into play quite nicely when you create like a lot of branches, like in this example over here. So the RefTable backend has been merged in Git 245 already, so last year. Naturally, though, getting RefTables merged was only a first step, and there's still a lot of things we had to do to get them fully up to speed. So where are we going with RefTables? The RefTable backend isn't really anything new. In fact, the whole effort to introduce an alternative backend into Git has already started 12 years ago in 2013. The project once again discovered that there is some kind of race condition when you want to pack references that could lead to inconsistent reads or like vanishing references. And it could lead to data loss. So we figured that it might be time to maybe think about a little bit better designed way to store references in your Git repositories. A first design to actually make the reference backend itself pluggable hit the mailing list in 2014. It wasn't yet really clear how the reference backend would look like, but there were a bunch of restrictions that we had. For example, databases like SQLite were not really an option because JGit couldn't use it natively. So we discarded SQLite as a backend. Also, several other databases were not really an option because of licensing concerns, because they were simply incompatible with Git itself. The next 2 years were then spent on slowly refactoring the Git code base to enable pluggable reference backends in the first place. In 2017, we then had the first RFC for the RefTable backend, as well as an initial implementation in JGit. The technical documentation for the format landed in 2020. The RefTable library to write and read RefTables landed in 2022. And finally, the RefTable backend itself landed in 2024. So this is the kind of huge odyssey that you can actually expect in the Git project if you want to upstream a big change into this project. But upstreaming the backend to Git was only a first step, and there were still a couple of things that we had to do afterwards. The first obvious one is performance optimizations. The files backend had 20 years of performance optimizations in the past. And initially, the focus for the RefTable backend was not to get it fast, but to get it correct. So while the RefTable backend should be faster in a lot of use cases in theory, there were still edge cases, and there still are edge cases where that's not actually the case. One of those cases where the RefTable backend should be significantly faster is when you write many references at once. For most of the part, this is because with the RefTable backend, you end up only writing two different files, the new table and the new tables.list file. So with that knowledge, I was very surprised when this specific email here landed in my inbox. Brian claims that when deleting all the references in a repository and recreating them, then the RefTable backend is significantly slower compared to the files backend. In fact, more than 50 times so. Now, we may agree that deleting 50,000 references only to recreate them might not really be the most typical use case that you end up doing daily, but it still very much left me puzzled. As it turns out, this was quite an interesting edge case overall. With the RefTable backend, the deletion does not actually end up deleting the reference immediately. Instead, you end up creating a new table that contains a tombstone for the reference that basically marks it for deletion. This is in contrast to the files backend, where you indeed end up deleting the deleted reference immediately. But with the RefTable backend, we only decide to merge the tables at a later point in time, and it's only at that point in time where the reference will be truly gone from the whole stack. But why do we even care about that? The answer here is conflict checks. Whenever you update a reference, we need to verify that there are no references with conflicting names. So for every reference, we first have to check whether there is a reference that has the same prefix, or whether the reference itself is a prefix of another reference. This is obviously cheap in a repository where there are no references, because all reference lookups will simply yield nothing. But with the RefTable backend, we first have to determine that a specific reference has actually been deleted with a tombstone, which is significantly more expensive. So how did we fix this issue? In Git, we introduced batch conflict checks. Previously, we always performed the conflict checks for every single reference individually, which had the effect that we would check 50,000 times whether refs had sum exists, whether refs hats exist, and whether refs exists, which is quite a waste of time. But with batch conflict checks, we don't have to check refs hats again if we have already determined that it already doesn't exist. And this indeed led to quite a significant speed up. Where previously it took 80 seconds to create 10,000 previously deleted references, it now only takes 11 seconds. This still isn't really exactly great, to be honest, but it's a significant improvement at least. Another area where the RefTable backend is lacking is when performing many separate reference updates in separate transactions. For every single transaction, we not only have to write the new table and tables.list file, but we also have to perform auto-compaction to ensure that the list of tables is kept at bay. But there are a couple of use cases where we actually have to create multiple transactions. And the added auto-compaction is quite costly in this context. So one such use case is fetches. Whenever you execute git fetch, we update each reference in a separate transaction. This is done because if we fail to update one reference due to whatever reason, we still want to proceed with all the other reference updates. But unfortunately, reference transactions are atomic. So we either update all references or we update none of them. So they are not really a good fit for this specific use case. So to fix this gap, we introduced batch updates into Git. All reference updates are part of a single transaction, but we now mark that specific transaction so that it's allowed to fail part of the reference updates while continuing with the rest. So after the fact, we can then figure out which references have been updated successfully and which one have failed, but the overall thing will still happen in a single transaction. So we updated GitFetch to use this new mechanism, which again leads to quite a significant speed up. Before, fetching 100,000 references took around 40 seconds. With the changes, it only takes 1.5 seconds. Furthermore, this new mechanism was also not only applied to GitFetch, but also to Git receive pack, which is basically what is used on the server side to accept your pushes. And I also very much expect that we will apply this optimization to other areas in Git as well. Another similar use case is when you rename a remote. After rewriting the Git configuration to have the new remote name, we also have to rename every single reference one by one to have the new remote name in it. This operation, as it was in Git, is not even remotely atomic. If any of the renames failed, or if the user, for example, canceled the rename operation, then you're left with a partially renamed remote. But besides being non-atomic, this is also extremely slow. When you rename a remote with 100,000 branches, it takes a lot of time. You can watch even how every single reference gets renamed. So how long does it take? This specific example here takes more than an hour to rename the references. And it ends up writing 186 gigabytes of data to your disk, which is kind of stupid. The funny thing is, this isn't even using the RefTable backend. This is actually using the files backend. The problem is that every single time you want to rename a reference, you first have to delete it from the packed.res file. But the packed.res file with 100,000 references is around 7 megabytes, and you have to do that 100,000 times, which is, of course, very slow. The RefTable backend doesn't really perform very well in this specific case either, but it's still significantly faster because it doesn't have to rewrite all the references every time because of the tombstones and because of geometric compaction. But we again tried to solve that, and we again converted it to use a single transaction where we basically batch all the reference updates into one. So we only have to rewrite the packed files file once, and for the RefTable backend, we only have to write a single new table and append it to the tables.list file. So these performance graphs here are for the RefTable backend. And as you can see, for 100,000 references, it previously took almost 10 minutes. That's way faster compared to the files backend, which took more than an hour, but still not exactly what the user expects. But after the change, we now only require 12 seconds. So this is only an excerpt of the different performance optimizations that we did over the last 2 years. And there's a lot of smaller optimizations left and right. But overall, the trend is quite clear. We iterate a lot on performance, and we'll also continue to do so in Git. So how does the backend perform against the files backend nowadays? Quite well overall, I would say. So this is, again, only an excerpt of benchmarks, and real-world numbers may look significantly different, but in most cases, the RefTable backend is either on par or significantly better than the files backend. There's one exception, though. When writing many references sequentially in separate transactions, then we're still slower compared to the files backend. But this is mostly due to the added auto-compaction. So the end result for this specific benchmark with the files backend is a very unoptimized state, whereas with the RefTable backend, we actually come out with a fully optimized database. So it's a little bit apples to oranges comparison here. And one thing to highlight here is also the last comparison, which is not an error. With the files backend, deleting a reference scales linearly with the number of references that you have in your repository. But with the RefTable backend, you only have to write the tombstone, and then you're done, so it's basically constant time. Sure, go ahead.
So I'm curious, like the one slow case there.
Sorry, 1 second. We need to pass on the microphone.
I'm curious, thanks for this presentation, it's great. The sequential graphs there, where
It certainly is specific to the file system that you're using. It was on my laptop, it was an X4 file system, so other file systems might look significantly different. Like, it basically, like for the file, for both backends, it very much depends on how fast you're able to like write single files and so on, but it will definitely vary. It's not production measurements here.
Thanks.
Okay, so let's move on to tooling, because that is also one of the things that we worked on a bunch over the last couple of releases. So as I've said, RefTables is basically a binary format. So it becomes infeasible to just paper over gaps in Git's tooling by going to the file system directly. But one such use case where users didn't have an option is with reflogs, which basically store a log of operations you perform on specific references. It wasn't even possible to list all the available reflogs in your repository without going to the file system. So we introduced new tooling to list available reflogs, manually write new reflog entries, but also to delete a reflog altogether. In Git 246, we also introduced new tooling to migrate reference backends for existing repositories with Git refs migrate. One initial gap, though, was that you could not migrate repositories that contain reflogs, like most client-side repositories actually do. But this limitation has also been lifted in Git 249, so you can nowadays also migrate those repositories. And if you want to be daring, you can nowadays also tell Git to use the RefTable format by default by setting the init default ref format configuration. So if you set that, then every time you use git init or git clone, then we will use the RefTable format by default. But that leaves one more elephant in the room, which is basically the ecosystem. There isn't only one implementation of Git, but there's multiple ones. So who else can use RefTables? For now, it's unfortunately only JGit, which is also where it has initially been implemented. But recently we have finished implementing a fully working backend for libgit2, where libgit2 is basically a linkable library for accessing and writing to Git repositories. One important user of libgit2, for example, is Cargo, which is the official package manager of the Rust ecosystem. This work is split up across 5 different pull requests, adding around 16,000 lines of code, none of which have been reviewed or merged yet, but hopefully sooner rather than later, libgit2 should have that backend as well. The next one that I want to tackle is probably Gitoxide, which is a Rust implementation of Git. But for now, I'm still constantly fighting with the borrow checker, so it will probably take a little bit of time before I'm able to land that one. So RefTables are supposed to be a drop-in replacement for the files backend. So in the best case, you shouldn't really notice any difference. So that raises the question, why should you actually care about that? The first one is file system encoding issues. With the files backend, we were subject to a lot of different specifics of how file systems work. Reference names are directly derived from path names, which generates various different issues. For example, you cannot have references that only differ in casing on a case-insensitive file system like on Windows or on macOS. Second, file systems like, for example, HFS Plus on macOS may decide to change the representation of a file if it has Unicode characters in the path name. So the reference name you want to store on the disk and the reference name that actually gets stored on disk might actually be different. And also, some file systems won't allow you to create branches that are called, for example, COM1, because for some Windows folks, this is seemingly precious memory. So with RefTables, all of these issues actually go away because we don't use the file system paths anymore. The next one is improved performance. While I very much hope that most of you don't have to work with repositories that have millions of references, if you do, you might very well appreciate the improved performance that RefTables actually bring you. The last one is also that the files backend does not allow for atomic updates or also atomic reads or consistent reads, because references are written one by one to the file system. This issue goes away with the RefTable backend, where both reads and also writes are fully consistent and also atomic. You probably don't really care about this too much on the client side, but especially on the server side, this is something that is really important. And last but not least, RefTables will actually become the default in Git 3.0. So if you use Git in scripts, for example, or if you use Git on the server side, then you should verify that you don't play any weird games by, for example, accessing the references directly on disk. You should always use or access references by using Git commands or a proper library if they have the Git backend or the RefTable backend. And if you do so, you shouldn't really notice any difference. So this is all I have to say about RefTables today. I would definitely appreciate if you could maybe give RefTables a try and play around with them. If you find any bugs, don't hesitate to reach out to me. Just send me an email, and I would be very happy to have a look at that specific use case. I don't know if we still got a couple of minutes left. If we do, is there any questions?
Yeah, so we got also questions from online, from YouTube, people watching the movie, right? Let's start with the room here. So,
Let's pass the magic microphone around.
I'm curious, during compaction, what happens to the files that have to be deleted? Is there a time span by any chance, like to delay the deletes?
It depends. In theory, those get deleted immediately, which is especially a problem on Windows systems, because on Windows you typically cannot delete a file that is still held open by any other process. So what we do there is, if we cannot delete it, we basically just ignore it and keep it around on the disk, and the next time around somebody tries to do auto-compaction on the stack, they will delete the old files. And on, like, when you then want to read the RefTable stack, and at the same point in time one of the files vanishes, then you can basically retry, reread the tables.list file and then retry with the new